About what happens to a crystal when we apply a DC bias across it. So we talked about it and we saw that the particle is going to do some block oscillations. Yep, we talked about it, how the vector k is going to evolve because h bar dk by dt is equals to force. So this is a semi-classical model of the electron moving in a crystal as a wave packet. So the center value of k of the wave packet, that varies in time through this equation, right? So this is like force is equals to rate of change of momentum. Instead we have crystal momentum here. H bar k is crystal momentum. And now because my k evolves with time, right? So this E is simply some constant electric field because I have applied a DC bias, so E is going to be constant. It's not E basically, it's Xi. Okay. So this is constant, so you can simply integrate it, you get K as a function of time. And if my Xi is negative, electric field is negatively oriented, your K will increase with time, linearly increase with time. So say if you start here, k0 is 0 and you start here at t equal to 0, then your k starts to increase. Okay, if k changes, then Vg is also going to change because Vg is d, okay, 1 by h bar should also be there. So but Vg is proportional to d by tk. If my k is changing, so my d by dk will also change. What is d by dk? If you have a band like this, its derivative is going to look like this. Yeah, so you have all the positive slopes here, so you have a positive velocity. You have a 0, 0, right? A 0, if you draw a line here, so that will give you 0 slope, so you have Vg0 here, and somewhere here you have a maximum. So this is a positive one. Here you have a negative one. Here you have negative, positive, because it's periodic, so it's going to look like periodic. E versus k is periodic, so dE by dk will also be periodic. Right, so then we talked about how the particle's trajectory is going to be. So it's going to oscillate. If k keeps increasing with the application of force, so Vg first increases, so particle moves fast, reaches the maximum velocity, then it slows down, then it changes the direction when velocity becomes negative. Then again its velocity increases in the negative direction and then it comes back. Okay. So if you talk about the position of the particle, because there is a change in the direction of the velocity, so you will have some oscillation. So particle increases, its velocity increases, slows down, then the direction of the velocity changes, so it will return, it will move back, and it's going to happen periodically, so it will oscillate. Yeah, so we saw all of that, but then we also talked about this does not happen practically. If you have a say copper metal and you apply some field across its electric field, constant DC bias, you don't get AC current. I mean, DC gives you DC. If the particle is moving, if it is oscillating, then it's some kind of an AC current. In fact, on average the current will be 0, because half of the time particle is moving in one direction, half of the time it's moving in other direction. So on average, if you see, it will give you 0 current. Does that happen? It means copper should not have any conductivity. That doesn't happen. Copper does have a conductivity. When you apply the electric field, there is a unidirectional flow of the current. Depending upon the direction of the electric field, you will have the flow of current, right? If you apply say positive voltage, negative here, right? So what will happen? You will have a current from positive to negative. Right? But what does this theory say? The theory says if you have a perfect periodic crystal, you should not have any current. On average, the current should be 0. You should not have any conductivity. So then we talked about that's not the reality. We don't have a perfect periodic crystal, by the way. We have crystal with non-idealities. What are those non-idealities? There might be some defects. Okay, so if the k increases a little, particle is picking up some k, it's picking up some velocity under the application of force, but then it gets scattered because of the defect. It's moving, but then it sees some kind of a bump, some kind of a non-periodic thing, non-periodic potential, so it will get bumped, it will get scattered, and whatever k it picked, it may come back to 0. So it started somewhere here, but its k came back to 0. But remember, the particle still covered some distance. If I have this and this, right? Say particle starts here and you have a scatterer here. You have some scattering potential here, some defect here. The particle still moved from here to here. So it picked up some k, scattered, its k become approximately 0 because it transferred the energy, right? But it still covered some distance. It will again pick some k under the action of force. If my electric field is negative, k is going to still increase. So it will again pick some k. There will be some other scatterer to stop. But it has covered this distance. Right? So particle is still moving in one direction. Always remember that. What do we want for the conductivity to happen? There should be a non-zero current. There should be a non-zero flow of charge in one direction. Net flow of charge in one direction. It picks up some k, comes to 0. Again picks up some k, comes to 0. So it is still traveling. It is still traveling from one end of the crystal to some distance. Okay, so it's giving you some current. Yeah, so that's the reality because of the defects. Now that's a very weird thing. Normally, what do we think? Whenever you have non-idealities or the defects inside the crystal, what do you expect? It's going to increase the resistance. That's what you expect, right? Whenever you have some non-idealities, some non-periodicity, you think that that's a bad thing. Yes, it can be a bad thing, but that's necessary for a non-zero current. That's necessary for your conductivity to happen. If you don't have these defects, you can't have conductivity. That's the reality. Okay, so these defects are giving you some conductivity, because otherwise what will happen? If you don't have these defects, what will happen? The particle will go like this, will return. Go like this, will return. This is not conductivity. You don't have a unipolar flow of the current. Right? So you need these defects. You need your crystal to be some non-idealistic. Now if you have lot of such defects, then that's a separate thing. Then they will reduce what we call as the mobility, so they will reduce that. But the presence of these defects is necessary. Okay. Okay, so we talked about it. So this gives you, so we talked about the energy bands. Now we are moving towards the current. We are trying to create some connection with the energy band and what will happen to the conductivity. Right? This is just an example of that. Let's talk about the conductivity in more detail, more thoroughly. Okay, so let's talk about what happens to the electrical conduction at temperature equal to 0 Kelvin. When my temperature is equal to absolute 0, what will be the conductivity? What will be the electrical conduction? And I am not applying any electric field right now. So say I have this simple sample of the crystal and the DC or AC bias is 0, no electric field, no external force, and what will be the conductivity or the conduction in the crystal? Can there be a conduction in the crystal in those circumstances? Let's see. Okay, so what kind of picture I will have at capital T equal to 0? So this is my EK diagram at capital T equal to 0. Now let me I'll talk about how this is blue, and how these are some empty states you see here, right? So this is the filled, this is the empty. So you have two bands. Assume that you have an atom. So your crystal is made up of some atoms, and we have just two bands. Let's just assume that, right? In reality, there can be multiple bands, right? So, but let's talk about a very simple case in which you have simple one lowest band, then you have this higher energy band, and then you can have more bands with some higher energies, right? So we talked about it in the Crony-Pany model, right? So you get some lowest energy band, then you get higher band, then you will get again a band like this, then again a band like downward parabola, upward parabola. So it's a sequence. So let's talk about the lowest energy band and the band just above it. Okay, and let's talk about what kind of system we have. So let's our crystal, say our crystal has n number of sites. It's a 1D crystal which has n sites, and there is one atom per site. So every site has one atom. Okay, so like this. So you start from here. There is some lattice constant A, and at every site you have one atom. Simple picture. Okay. Then assume that an atom contributes, say, 2 electrons. Okay. Let me assume that it's a very simple atom, and one atom, in the outermost shell of the atom, we just have 2 electrons. The rest of the electrons are core electrons. We won't talk about them. They kind of don't take part in the energy band formation, right? Most of the splitting of the energy band happens through the interaction of outermost shell electrons. So say in the outermost shell of the atom, we have just 2 electrons. So 2 electrons can participate in the form of in the formation of energy bands. Yeah. Now we have to fill the electrons, the total number of outermost shell electrons in the system, into these bands. So what are these bands? These are energy states. Every k is one eigenfunction, right? So how many you have? So this will be minus pi by a to pi by a. It's like your first Brillouin zone, and in one Brillouin zone, first Brillouin zone, how many k values do you have? How many k values do you have in one zone? If you have n number of sites in a crystal, then how many k's do you get? Through the periodic boundary condition, we saw that we will get n k states. In the Brillouin zone, we will get n k states. Yes, remember 2 pi by L. L is your n times a. So 2 pi by Na is the difference between two k values. You have these k values through the periodic boundary condition. What did we get? The difference between these two k values was 2 pi by Na, or 2 pi by simply the length of the crystal. Yeah, just recall that. So these, if I count them, so they will be equal to the number of sites. Okay, now I have to fill these electrons. Now remember that I have temperature equal to 0 Kelvin. So electron does not have any thermal energy at all. No thermal energy. Yeah. How will the filling of electrons happen? Now also remember that corresponding to 1k, so you have one block wave. Yes, one eigenfunction which is block wave, which is some u into e to the power iota kx. But there is another degree of freedom an electron can have. So for the same k, you can have two types of electron with up spin and down spin. So spin can also be another degree of freedom. So basically for 1k, you can have two wave functions, one with the up spin, one with the down spin. So it's simply going to be, say if you have this u x into e to the power iota kx, right? So you will simply multiply this with some spin part. So this is, say, up. Okay, and similarly you will multiply this with some function e to the power iota kx with this. This is some function which is different for different spin. So for 1k you can have two eigenfunctions. In the Schrodinger equation we did not consider the spin, but it's a simple, you can simply remember it as, for 1k you will have two eigenfunctions. Now it means 1k state, any of this k point. So if I say this point, right? So this particular point can hold two wave functions. It means two electrons. Correspondingly, say I have a minus k, that can also hold two more wave functions with two different spins. Yeah. So how many k values I have? N. What is the total number of electrons I have? So one atom contributes 2. So I have 2n electrons in total. And I have to distribute those 2n electrons among n k states. And each k state can hold 2 electrons. What will happen? I will start filling the electrons starting from the lowest possible energy. Right? I will keep increasing the energy, will start filling the electrons. So the 2 electrons go here, 2 electrons go here, then 2 electrons go there, 2 electrons here, 2 electrons here. My lowest energy band in this particular case, that will become completely filled. Why? Because how many points are these? Capital N. And how many electrons do I have? 2n, and one state can hold 2 electrons, so this is going to be completely filled. And the band number 2, that's going to be completely empty. Highest filled band at T equal to 0 temperature, it's called valence band. This is the valence band. And the band which is just next to the valence band, which is empty at T equal to 0, that's called conduction band. Why conduction band will become clear. Okay. So let's see. Now I have electrons only in this band number 1, and every electron has some k. It means it has some group velocity. So there is some wave packet whose center k is the k here, right? So corresponding to each k you will have wave packets, wave packet of electron, right? So there will be two, because of plus and minus spin, but let's assume that spin is equals to, say, 1. So let's just ignore the spin. So you have 1k, and corresponding to that you have one wave packet, okay, or maybe two wave packets, say, for if you want to include the spin. So this wave packet will move with some velocity. So what's that velocity? dE by dk, 1 by h bar dE by dk. Yes. So it will have some group velocity. So every k state has some group velocity. So every electron is moving. We already saw what kind of velocities we will have. So what will be the velocity of these electrons? What will be the sign of the velocity? So this will be what will be this? 0. We'll start from the 0 velocity because the slope is flat, right? And what's the slope here at any generic point? Negative. So all of these states are moving in the negative direction of x-axis. So Vg is negative here, right? So all of these electrons are going to move in the negative direction. All of these states have positive slope, positive velocity. So all of these electrons are going to move in the positive direction of x-axis. Now let's try to calculate the current. Corresponding to each k, you have a wave packet which is moving with some velocity and it is contributing to some current. How much current it will contribute? If the length of the crystal is say L and it's moving with a constant group velocity. Group velocity is, by the way, for one particular k, the group velocity is d by dk, and I am not applying any force, so your k remains the same. K at t equal to 0 is going to be k at any t, because external force is 0. Right, remember dk by dt is equals to force. If I have 0, so k is going to be constant with respect to time. Only then you can have a 0 derivative. So every electron in a particular k state has a fixed k. It doesn't change with time, and because of that fixed k, your dE by dk, which is proportional to the Vg, that is also fixed. So electron is moving with some fixed velocity. Now how much current one k state is going to contribute? Can you tell me? If the length of the crystal is capital L, so say this is the length of the crystal. How many electrons are there in that k state? 2 electrons. So the charge is 2e, minus 2e. What is the definition of current? Rate of change of charge, dq by dt. Yes? So how much charge passes through a point in time dt, that is your dq, and dq by dt gives you the current. Or this will also work. If I have a point and in delta t time, if delta q amount of charge passes through that point, I get some current, which is delta q by delta t. I have 2 electrons. Yes, say I talk about these electrons with say positive velocity. They are traveling from, say I talk about a particular k state here. So this is moving like this. So there is some movement of charge. There is a movement of charge is going to contribute to some current. How much current? Can you calculate the current? What will be the current? What will be the current? If my velocity is Vg, charge is minus 2e, what? Vg? Vg by L. You forgot one factor. If my charge is traveling from here to here, how much current it will contribute? You have to simply calculate delta q by delta t. So simply, see, you can do it like this. Delta q, amount of charge, say I multiply and divide it by some delta x. So what is this? Vg. You need to calculate this. So 2e amount of charge passes, so it travels from here to here in time, say delta t. So what will be this thing? So what is the charge? Minus 2e. What is this? L. What is the velocity? Vg. So this is the current contributed by 1k state. 1k state. Yes? How much is going to be the total current? You need to do the summation of currents contributed by all the electrons which are there. All the electrons. How much will be that current? So current is always some charge density times velocity. In this case, you have 2e divided by L. So you are calculating some kind of density, right? Charge divided by, because it's one dimension, so you have length. If it was say 2 dimension, so it will be some kind of area. If it is 3 dimension, you will have some kind of volume density. Okay, per unit volume. So it's always of this form, some velocity into some charge density. So dq by dt will give you this. So we saw that. So it's giving me minus 2E by L into Vg. The total current is going to be, so in 1D the current density or current, it means the same. So maybe in your notes I wrote the current, but in 1D current or current density is same. Current density is J, current is I, right? So usually you have current density equal to current per unit area, but you don't have an area in the 1D, so current density and current are basically the same thing. In general, we may talk about in terms of current density. Okay, so the current is going to be simply minus 2E by L into Vg, right? So this is the current. What is the total current? Total current is going to be what? So you will have to sum up all these currents over the all filled states. Yes, how many filled states we have? I mean, filled state means the state which have electrons. All of those states will contribute to current. These will not contribute to current. These are empty states. There is no electron in that. The only states which have electrons, and those are moving electrons, they will contribute to current. So you will sum up over this, the field. Now in this case, what is the field state? So all the states in this zone are filled. So instead of field, I can also write zone here, because all the state in this zone at capital T equal to 0, temperature equal to 0 are filled. So field is equivalent to zone here, right? Zone means you are going to sum up with on all the k states in this zone, starting from here to here, minus pi by a to pi by a, right? All of those k. Okay, so this is the current. Okay. Now let's now k is almost continuous, right? We know that k, the difference between two k values is what? So you have this minus pi by a to pi by a, you have this zone, and the spacing between any two k values is 2 pi by L. It means 2 pi by Na. Okay, this we got from the periodic boundary condition, and capital N is large. We're talking about a lot of atoms. We're talking about a crystal. So this spacing is going to be very small, so I can assume that k is almost continuous, right? K is almost continuous. So the spacing is very, very small. If my spacing is continuous, I mean spacing is almost 0, so this summation I can actually convert it into an integration also, right? Summation will get because what are you summing on? You are summing on k's. These k's are very closely spaced. So this summation over the zone, this will become an integration. Now how do I convert this summation into an integration? I will say I have some width dk here. Okay, this is the small range of k, right? And I will check how many k states are there in this dk. So 2 pi by Na or 2 pi by L, it contributes to 1 k state, right? So these are n points here, right? And the difference between the two k values is 2 pi by L. So I can associate one particular cell to one point. So this is associated to say this is associated to this is associated to this. So you can say one cell width is associated with one point. So if you have n sites, so you have n such spaces. Roughly, I mean there can be n minus 1 or n, depending upon n is even or odd, but when n is large, n minus 1 or n, they are equivalent, right? So don't worry about it. So one spacing corresponds to 1 k state, right? If you have n, so you will have n such spacings. right? So 2 pi by L, this much width correspond to 1k state. Dk will correspond to how many k states? How many k states will be there in this dk? This much contributes to 1. So dk will contribute to dk divided by this thing, right? Yes. So number of k states which are there in this width dk are this, and because the variation in the k from here to here is small, I mean I have shown it with a larger thing, but dk is actually small. 2 pi by L is very small, but dk I have chosen, it's like it is small, it's larger compared to 2 pi by L, but it is still much smaller compared to the zone width. It's much smaller compared to 2 pi by A, right? So in dk you have dk by 2 pi by L number of states, and because k is almost the same from here to here, so you can associate the same Vg to all of these. So how much current you will have? So 1k state used to contribute to minus 2q by L into Vg. These many states will contribute to how much current? Dk divided by 2 pi by L, this is the number of states, and all of these states have the same velocity Vg, and you will also have this minus 2q by L. So this is the current contributed by the states which are there in this width dk. Got it? Now what do you have to do? You will have to sum up all of these dk currents over this dk. And what do you get? You get integration. So if you sum up all of these, so you get integration. Integration over where? Over the zone. Okay. Let me just erase this, and okay, so you have this thing. That's what I wrote, right? And Vg is a function of k. Okay, so dk by 2 pi Vgk, and that L, where is that L gone? So this L and L will cancel. So there is a minus 2q by L, and there is a 2 pi by L coming. So these are cancelled. So this will become minus 2q into dk by 2 pi into Vg, integration over the zone. So that's the current. That's the current carried by all the k states in the band number 1. What is my Vg? My Vg is dE by dk. Yes? This is not iota, this is 1. Okay, 1 by h bar dE by dk. So that's what my velocity is. What will be the integration? Can you tell me? So let me show you the picture. So this is the band. If you have this type of a band, right? Although we had inverted one, earlier I showed you something like this, but let me just take an example of this. I did not have another figure for that. So if you have a band like this, so we know that in half of the zone the velocity is positive, in half of the zone velocity is negative. We all just saw that, right? So if you have a k point with this particular velocity, you have a corresponding k point with this negative velocity and equal magnitude. So when you are integrating this thing, what will happen? Positive k and negative k, they will cancel because it has plus Vg, it has minus Vg. Any k in the 0 to pi by a will have a corresponding k in minus pi by a to 0, which will cancel its contribution. So this is going to become 0. You have 0 current when you don't apply any electric field. Okay, you have 0 current. Now I haven't even put any restrictions over k right now, right? So that those block oscillations they will not come into picture because we are not even applying any electric field, right? So this K is just K, so 1K will carry Vg forever. This is, by the way, a very different picture from, so I don't know if you have heard of a model called Drude's model. The Drude model is your conventional model. You might have studied that in your high school maybe, not by the name of Drude model, but it's simply a model like, so you have a classical model, you have some atoms and you have electrons, so electron gets bumped into the atom, right, scatters, and then it increases, its velocity increases. If you have applied the field, it gets scattered. If say you haven't applied any electric field, so then we say that electron has this random thermal velocity and it's just moving randomly and it will give you zero current. So that's the classical picture, but quantum mechanical picture is this, right? So you have K and there is a corresponding minus K which has the negative velocity, and that gives you zero current. But in each K state you still have Vg, a constant Vg. It means the electron is, see, you have this crystal potential, so there are atoms, but when electron is interacting with the crystal, it's not like it's physically dumping off or anything. The overall picture is that the electron is a wave in the crystal as a block wave, and it is giving you a fixed Vg, and the Vg is a fixed quantity. It's not like it's bumped into the crystal, it became zero, and nothing like that is happening. Vg is there forever. So it's a little bit different picture. Not a little bit, it's a drastically different picture, the quantum mechanical picture. Okay. Anyhow, so what we get is a zero current at t equal to 0. Okay. Now let's talk about the concept of holes. Why I showed you that picture, because that's going to help you understand the concept of holes. How many people already know what a hole is? Not like in the quantum mechanical, but just semiconductor has electron and holes, right? Yes, I think most of you already know what a hole is. It's like an empty state in the bond. That's how the first thing that comes into our mind when we think about a hole. But where is this concept coming from? Why do we say that, oh, hole is there, it's a positively charged something, right? It's a fictitious particle which moves with a positive charge. Where is this thing coming from? So that again comes from the quantum mechanical picture I'm going to show. The concept of hole is coming from the picture, the quantum mechanical picture. So okay, so now let's talk about a temperature which is not equal to 0. So this is a temperature which is non-zero. What will happen? Some of the electrons will get enough thermal energy, and the states which were filled here, they will become empty and they will reach this higher energy band. Okay, some of these electrons will simply get this thermal energy and reach here. And why I took only the electrons which are near the top? Because they are the closest. They are the closest to this next band. This electron, if it has to go from here to here, it will require a lot of energy, lot of thermal energy. But this electron will require the least amount of thermal energy. This will a little more, this a little more. So only the electrons which are near the top, they might be missing at some non-zero temperature, depending upon how high the temperature is. The temperature is very high, a lot of electrons will be missing. If the temperature is not that high, a few electrons will be missing. Right? But the fact is, there will be some empty states here, and the states in the next band, band number 2, they will become filled. So that's the picture we have. Now instead of one band, I have two bands. Band number 1, band number 2. And the current is now going to be contributed by filled states in band number 1 and filled states in band number 2. Each of the field state has some k. If they have some k, they have some velocity, which is d by dk. If there is a velocity, there is a movement of charge. If there is a movement of charge, there is a current, at least locally. Okay, so let's talk about the current carried by the electrons in, say, band number 1. So J1. So now I'm going to be integrating over the states which are filled in the band number 1. So field 1 means the states which are filled in the band number 1. So I will not integrate over this, I will only integrate this. Okay, and the group velocity I have denoted as Vg1. Yes. Okay, now we already know that if my band would have been completely filled, if this band 1 would have been completely filled, I get zero current. We know that, we just saw that, right? So if I write the same integration, but instead of the filled states, I write zone here over the complete zone, assuming that if these states were also carrying some electrons, then if I integrate over the whole zone, that will give me 0. Mathematically, that means this. If I do this integration, we just saw that over the zone, if my k varies from all the values from minus pi by a to pi by a, all the values in the zone, if I consider, then this gives me 0. I know that, right? Can I split this integration into 2 parts now? Because it's just a summation, so I will now distribute my zone into 2 regions. So first region is going to be the states which are filled. The second, I can say these states which are right now empty or unfilled. So I can write this. The whole integration can be divided into 2 parts. Integration over the filled states plus integration over unfilled states. Correct? This thing is 0, we know that. This thing is my J1. So what do I get? This is 0, this is J1, I get this, right? And I can write J1 in this form as well. So J1 in this form, if I write in equation number 1, I have integrated over the filled states in the 1, but here I have integrated over the unfilled states in the 1, but I changed the sign of the charge. I wrote plus 2q instead of minus 2q. Yes, it is as if only these states are filled, and instead of electron I have a fictitious particle which carries a plus q charge, and I am integrating over that. Yes? Yeah? If these states were carrying some particles, how would you write the formula for the current? Assume these are all empty and this is filled. How would you write the formula of the current? You will write 2q integrate dk by 2 pi into Vg. Okay, and what is the charge on those? It's plus 2q now. So the integration of the filled state with electrons is equivalent to the integration of unfilled state, integration over unfilled state with some fictitious particle which has a plus q charge. But 2 is coming from the spin, so don't worry about that. So it's a plus q charge. Okay, so that fictitious particle is called hole. So that's where the hole is coming from. Okay, because the description is equivalent and it is easier to deal with the small number of states than these large number of states, right? I have to integrate over this and this. Here I have to just integrate over this. I just need to worry about the small number of states which are empty. I have to just change the sign. Okay, so this is called hole. One empty state will carry two positively charged holes. One K corresponds to two holes, plus spin and down spin, okay, because there are two here. Yeah. Okay, so we'll continue from here in the next class.